So good afternoon, everyone. Welcome to this last session of today, and thank you to Alejandro and UPM for the organization of this workshop. There is a change with respect to the program. Now we have the presentation of Dr. Rodolphe Vaillon, Professor Rodolphe Vaillon of CNRS, and this presentation was scheduled for tomorrow, but we have a little variation with the program. Dr. Vaillon is a CNRS professor. His current main research interests are the development of thermophotovoltaic devices and the thermal behavior of photovoltaic devices. Now he will go to present the presentation. The topic is thermophotovoltaic energy conversion. So I give the floor to Rodolphe.
Thank you. So thank you very much for the introduction, and I would like to thanks Alejandro for inviting me to give this talk. So it was scheduled for tomorrow, the last talk about energy conversion. So because of the change, I will give this talk now. And I will start with a foreword about the climate change emergency. We didn't speak about that, but this is somehow why we are here. And then I will introduce thermophotovoltaics with respect to solar photovoltaics. Then I will provide the key challenges for performance. So we had already these key performance challenges with the presentation of Andrew, especially everything related to the losses and the relationship between the emitter and the PV cell, the coupling of these two parts of the system. Then I will provide an overview of the state-of-the-art thermophotovoltaic devices that are available, and I will speak about some advanced concepts which are on the way, and I will end up with some prospects and conclusions. So very recently, it was 10 days ago, there was this very nice paper, one more paper about world scientists warning about the climate change emergency. So they were stating that we have a moral obligation to warn humanity about what we are facing. And this paper was signed by more than 11,000 people. So I suggest that you read this paper. It's very clear. So there is an urgent need for urgent actions. Otherwise, we are going to face very, very bad issues. And about energy, so this is very obvious, but the world must quickly implement massive energy efficiency and conservation practices, and must replace fossil fuels with low-carbon renewables. So we see on this graph that, unfortunately, since the 80s, the consumption of fossil fuel is still growing, both for oil, coal, and gas. So even though the increase of the use of solar and wind energy is much larger, it's still too small, and unfortunately, there is still an increase of consumption of fossil fuels. So we have to hurry up. So in this frame, so I think that this workshop has some key role to play, and the question is, what would be the role of thermophotovoltaics in this frame? So I'm taking this graph, which was made by Alejandro and Antonio Marti, about the different thermal to electricity converters. And we see that in the range of this temperature, thermophotovoltaic devices make sense because of the high efficiency. However, when we look at the systems which are commercially available, there are not so many of them. So one question is, why is that? Why are there so few systems available in the market? So first, what is the difference between solar photovoltaics and TPV? So in solar photovoltaics, the source is the sun, which is assumed to be a black body at around 6,000 Kelvin. But unfortunately, the radiation which is coming to us is coming in a very small Solin angle, so we have to use concentrating systems. And one important point is that this source is moving, so we have to adapt the collection of this radiation from this source because the sun is moving. Then the radiation spectrum is situated into this range of wavelengths, 0.2 to 2.5 microns, and it's not tunable at all. It is as it is because of the absorption of the species in the atmosphere, so we cannot do anything about it. So in terms of radiation fluxes, which is available without any concentration, it's 1,001 per square meter, but then you can use some kind of concentration. So everybody knows that the materials which are used for solar photovoltaics are mostly silicon dominating the market, then gallium arsenide, some CIGS, and the perovskite is growing in the market, but the most important point is that the band gap is in the range of 1 to 1.5 electron volts. So the difference for thermophotovoltaics is that instead of using the solar energy directly, which we could do, we are using wasted it or stored it, which is the point of this workshop. Then in between, so there you are some power input here, and you have an emitter which is at a temperature between 1,300 and 2,300 Kelvin. And the difference is that the radiation going towards the cell is comprised within the entire hemisphere. Compared to the previous case, this is one big difference. And then this radiation source is completely motionless. There is no moving parts, so this is much easier to handle it in terms of collecting the radiation. The most important point is that for the irradiation spectrum, it is ruled by the black-body spectrum, but on top of that, so it means that this is mostly infrared radiation, but you can play with it. This is completely tunable. So you can decide which part of the radiation you would emit and then collect in such a way that the cell will be the most efficient. So this is a big advantage compared to the previous one. Then in terms of radiation density, power density available, it's much, much bigger compared to the previous case. So let's say that you take a black body at 1,300 Kelvin, so you would have already 162 kilowatts per square meter. So at very much higher temperature, the highest one, so you are going to megawatts per square meter. So it might look an advantage, but in the end, you will have also very high currents. So you may end up with problems which are similar to CPV. So in that case, given that we are dealing with infrared radiation, we will use mostly compounds from the 3-5 groups, indium, arsenide, gallium, maybe antimony. And then the band gaps that we will be dealing with are in the range from 0.17 to 0.8. So this will be probably the most important slide of my presentation. There will be a lot of things. So I will try to show what are the losses coming with this kind of system. And then in the end, we will see that we need to optimize the emitter-cell radiation exchange. So first of all, we have to get some power in such a way that we'll have emitter at an equilibrium temperature that I will call TE. So this equilibrium temperature will depend on everything else, on how much this emitter will exchange radiation with the rest of the universe. Then, well, what you need is to have the heat from this emitter going through the cells and only by radiation. So it means that thermal insulation of the emitter is very important, and probably it might be an issue if you want to have some power in and not power out where you have the power in. So it's also mean that you need a view factor in between and the emitter and the cell of 1. So this is one very important point. Then, of course, you want radiation emitted by the emitter to be useful for photovoltaic generation. So what you should do is maximizing emission for the photon energy, which is larger than the band gap. So it means photonic engineering of the emitter. Well, you might also decide that, okay, there is some radiation with photon energy which is below the band gap going to the cell. So in that case, you have another option, is to reflect the radiation back to the emitter, then it will be recycled. So you can either do that or this somehow, which what it means is you have to have some kind of spectral selectivity in between the emitter and the cell. So this is a very important point. Then you want the power, electrical power, how to be maximized for the PV cell. So somehow it's making photonic, electrical, and thermal engineering. So for this, what you can do is first try to maximize luminescence, internal luminescence within the cell, which is common for photovoltaic cells. But then you can also maximize the luminescence up and somehow play. This is something that you cannot do for solar cells with the interaction between the PV cell and the emitter for the luminescence. Have some kind of photon recycling between the two. Then, of course, you should try to minimize the internal heat source because you will need to cool down the cell, and it might have some cost. So it means at the same time optimizing cooling, so maximizing, why not, thermal radiation up that might be recycled again by the emitter. And then you should have a minimum need for cooling, so it shouldn't cost anything or as little as possible for the efficiency. So why are we doing that? We want to minimize the temperature of the cell because everybody knows that when the temperature of the PV cell is rising, then efficiency is decreasing. So designing a TPV device requires all this to be optimized. Somehow this is what is important. So recently, well, not so recently because this idea was proposed a long time ago in 1967, but it was repeated in this recent paper by Omer this year. So the ideal regenerative thermophotovoltaic system would be like this. So you would have a thermal emitter in the middle of a cavity that would emit radiation. So for radiation with photon energy larger the band gap, so it would be okay. It would go toward the PV cell and that's it. But let's say that this emitter is also emitting radiation below the band gap, as I said before. So what would be interesting is to have a real reflector reflecting back as much as possible the radiation back to the emitter, then it would be recycled. So in that case, it would be almost a perfect system. So this is illustrated in the case where the emitter is a black body at 1,200 degrees C. And then you see that for energy below the band gap, because if you use a very efficient mirror, you will have most of this radiation not used for PV conversion, recycled by the emitter, so it's not a loss for efficiency, but at the same time you have less electrical power generated. For radiation above the band gap, so you have the distribution between the PV power and the usual PV loss. So it means that you have to play with radiation engineering, electrical engineering, and at some point, and which is very important, thermal management of all this system. It doesn't look so easy to do. So as Andrew already said, if you optimize the band gap and the mirror reflectivity, so you expect to have efficiency of this system larger than 50%. So now we speak with very interesting devices with a lot of efficiency. So now what are the state-of-the-art TPV device in the lab? This is the one. This one is already something like 15 years ago. The idea here was to use the monolithic interconnected modules to increase voltage. And you see that the back contact is connected to the top contact of the neighboring PV cell. And then the main point to achieve the efficiency of 23.6% was to design this reflector to recycle the infrared radiation back to the emitter. Then 14 years later, even though there were a lot of research done on TPV, there was this achievement of last year with also indium gallium arsenide. So this time the strategy is different. It's not about optimizing the reflector, but it's about optimizing the emitter. So in this case, you see the black body energy. A lot of it is below the band gap, so you don't want that radiation to reach the cell. So what you do is to have a selective emitter, which does this job, but it's not enough. Then they added a dielectric filter to cut this radiation, and this radiation with a wavelength much larger than that of the band gap. So with that, and also with a monolithic interconnected module, they reach an efficiency of 24.1%. So it was an increase of only 0.5%. So more recently, so last summer, there was this paper with a graphite emitter at 1,200 degrees C, also in gas. the band gap of all these record PV cells are within gas with quite large band gaps. Here they could achieve this high reflectivity mostly because of the rear reflector, which is boosting voltage for the photon energies above the band gap by increasing the extraction of luminescence. So this was an increase of the, let's say, the performances of the cell, and mostly by recycling infrared radiation back to the emitter. This is the idea that I was speaking about before. Now, if we want to look at the system, there are also systems called solar TPV. So the idea is to use the solar radiation to concentrate it onto an absorber. The problem here is that you will have unavoidable emission back that will not be used. This is one of the drawbacks of this system. And then this will reach an equilibrium temperature, and then we have radiation emitted toward the cell. So theoretically, Harder and Werfel demonstrated that with very complex, so the maximum concentration, high emitter temperature, and if you are able to maintain the cell at room temperature, we could reach something like 85.4% efficiency. Then Alejandro and co-workers and Algora in the room, they demonstrated, well, maybe we should go for a system that you could build, so a planar device with a smaller concentration and smaller temperature still. The efficiency that we could reach with this system is 45%. Now, the implementation of the lab, there were the first attempt with 1%, and then at MIT, another one with 3%, and the record is from the group of Evelyn Wang at MIT with 6.8%, with band gap which is a little bit smaller than usual. And here the strategy was to optimize the absorber. You remember that you need to absorb as much solar radiation as possible, and also to optimize the emission by using photonic crystals. But we see that still we are at a very low efficiency. That means that there are a lot of losses that I was speaking about before, that there is a system optimization required. Also, there are systems which are using as a source combustion of, recently also, I think from MIT, there was this micro combustor design, where here the strategy is to use indium gallium arsenide with an optimized emitter, again a photonic crystal, and a small size combustor, but in the end the efficiency was only 4.3%. At larger scales, it's not any better. So here the PV cell is a little bit different, but in the end the efficiency is still below 5%. So I have to cite also that there are some devices that have been built by JX Crystal, Mesodyne, which is connected to this result, and also MTPV Corporation, and now Entora Energy, but not using combustion, right? So the result, the message that I want to convey is that for a system there is a lot of optimization required. There are a lot of losses that need to be minimized. Now I would like to speak about the more advanced concept. I will speak about the near-field TPV. So the difference here, before I was speaking about an emitter which was far away or from the PV cell, means only propagative waves were emitted and reaching the PV cell. But as Alejandro said already, if you decrease the distance between the emitter and the PV cell below a distance which is smaller than the Wien wavelengths, this is the wavelengths where there is a maximum of radiation by the blackbody, which is at room temperature less than 10 microns, which is a challenge, then you will have the contribution of the evanescent waves. So this has been demonstrated many times experimentally. Here, this is one of the most recent results, 2016, where you have a planar emitter and a planar receiver. And you see that at 10 microns, the thermal conductance, which is the radiation conductance between the emitter and the cell, is constant in the far field. And when you decrease the distance between the emitter and the receiver, you see that this conductance is increasing big time with a factor which are on the order of 100 to 1,000. So what you expect is if you take benefit of this increase of thermal radiation exchange between the emitter and the receiver, the PV power will do the same. So this is an idea that was proposed at the beginning of in 2002 by Cravallo. And the first, let's say, convincing experiment that was made was only last year by Fiorino and co-worker, where you have a silicon emitter and indium arsenide PV cell. And you see here that, well, it's not really a PV, a photovoltaic effects, because we don't see the nice IV characteristics, but you see the increase of the power as the distance decreases down to 60 nanometers. So one challenge in this case is to have a temperature difference kept between an emitter and a PV cell at distances at the order of nanometers. And here they couldn't go above 355 Kelvin temperature difference, but you see that with this they could obtain a near-field enhancement of 40, which is amazing. But in the end, they could only estimate an efficiency which is below 0.02%. So there was another attempt, a recent attempt this year, where this time they use a silicon emitter. They put this intermediate to avoid, let's say, too much transmission of radiation below the band gap to increase efficiency, and they use an in-gas PV cell. And this time you see that you have nice IV curves with a much nicer fill factor of 0.56 and with a much larger delta T, well, a near-field enhancement which is a little bit more, but the estimated efficiency is still around 1%. So now this is a work which has been conducted in my current lab and previous lab in a project which is going on. We decided to take this strategy to go for the sphere-plane interaction, which is much easier to control in terms of distance in between the emitter and the cell. We decided to go for much lower band gaps than to use indium antimonide, but there is a drawback in that there is no way that you can make this PV cell work at room temperature, so we had to cool it down to 77 K. But in the end, the difference is, well, we are collecting much more radiation, so we are going to lower band gaps, which means a power density which is 3 orders of magnitude larger than the best previous case. But on top of that, we were able to measure an efficiency of 14%, which is a quite big leap forward, even though this is a demonstrator in the lab, so this is not a device. So we have here a substantial power density and efficiency. So it means that, well, with this kind of efficiency and power density, we can move forward for building devices. But the problem is, and it was already stated many times before, is when you have a very high power, radiation power, you have also very high currents. So you end up having issues with the ohmic losses. So this system was presented by Alejandro before. You can use the idea of hybridizing this TPV system with a thermionic system, where on top of the TPV generation, you have thermionic generation, which is the evaporation of electrons towards the anode, which is covering completely the PV cell. Then you totally avoid the resistive losses that you have before when you have a grid on a PV cell. So here, in that case, where a prototype is being built in the frame of the Amadeus project, you have both an enhanced output voltage, and then you avoid the problem of the grid when you have a very high powers to be converted by a TPV system. So the next one is to combine this hybrid system with the near-field radiation that I was speaking about before. And then in that case, as it was already shown by Alejandro in a simulation that we made last year, ideally, if you forget about these resistive losses, you should have a very nice enhancement only with the near-field TPV effect. But when you take into account the resistive losses because of the grid, the front grid, then everything is killed. But thanks to the hybridation of these with the hybrid hybridization with a thermionic system, then you completely remove this decrease, but on top of that, you have more power because of the combination of the powers of the two. But this system needs a demonstration that hopefully we'll be able to make in the future years. So now it's time for some conclusions. I would like to compare some kind of state-of-the-art for TPV. So in terms of emitter PV cell efficiency, we have reached something like 30% and probably more at Antara Energy, which means, well, now we are speaking. So it becomes viable for the market. But maybe I was only speaking about efficiency. We should have also better collection of radiation coming from the emitter. So maybe we might go for lower band gaps than the band gaps that were used in the examples I was giving in the talk. There is also the issue of the ohmic losses that we have when we have high temperature, and this is the situation in this workshop. So we should find solution to that. There are ideas on the way, and one of the ideas is the hybridization with the thermionic system. Now everything is developed mostly in the lab, and there are not so many or not at all commercial system. So how to go from the lab to the industry? This is some point that we'll have to address. In terms of system efficiency, whatever the system is with or without thermal energy storage, the efficiency is below 10% right now. So it means that we have to work on the optimization of the system from input power, but also to cooling. So it means a combination of photonic, electrical, and thermal engineering. And there are some promising advanced concepts that they are in the lab, I confess that, but there should be more prototypes in the lab for demonstrating the promises of these concepts. So with that, we feel that we should try, because the TPV community is existing for decades, and then there was a kind of decline. So we would like to build an international community again around TPV. So for that, we have decided to organize a symposium at the next European MRS conference next year, taking place in May in Strasbourg. So you are kindly invited to submit your work if you are working on TPV, of course. And at the same time, there will be a feature issue associated to this symposium published by Optics Express. So there will be a wide window for submitting your work in between the 15th of February to let's say 2 weeks after the end of the conference. So please think about it and submit your work. So with that, I would like to thank the funding of the project going on near-field TPD, and I'm ready to answer to your question. Thank you.
Thanks, Rodolphe, for your presentation. There are any questions? No question? Okay, I start. And I would ask you if you have some ideas to how obtain a distance of 60 or 100 nanometers for a commercial device.
Yeah, so there have been many works on making an experimental demonstration of near-field radiation, and there are more and more on them for the plain configuration, where one challenge is to build a standalone device where you wouldn't have to control the distance in between the emitter and the receiver. And recently there was a paper from different groups where they are using pillars in between the emitter and the cell to have a standalone device, and they could reach distance down to 150 nanometer. The problem is that right now the maximum temperature difference that they could achieve is still small, something around below 100 Kelvin. So the next challenge to be solved is to be able to do the same or something similar, and I'm sure that there are other ideas in different groups where you would have a much larger temperature difference between the emitter and the receiver. So this is a big challenge. But at the same time, I'm not sure that we really need to go down to so small nano gaps, or maybe 500 nanometers would be okay and would be already nice, especially if you want to reach high emitter temperature.
Thank you.
Very nice presentation, very interesting, Rodolphe. I was asking myself, and I'm surprised, that there are very few companies selling commercial products for thermophotovoltaic. I have seen that there's very few, JX Crystal or a few others. Why? Or the situation, the market is growing and there are growing other companies?
Well, probably Andrew would be able to answer to the question better than me. But anyway, since we are organizing this symposium, we try to invite these companies to come to this conference. And I had a conversation with one engineer from MTPV Corp, which has been around for some time. And in the end, they said, okay, you guys in academia, you are having a lot of ideas and very nice concepts. When you are coming to reality in making experiments, there is one huge problem related to the, let's say, high temperature emitter, and at the same time you have to keep as much as possible your converter at a reasonable temperature. And this was somehow, what I understand, is one key point for this industry to make this happen. And there is also these issues with insulation and not losing the input power to have this emitter at a given temperature. So there are so many engineering issues to be solved at the same time. So it means that it's not so easy. And then as far as I understood, MTPV Corp, when you look at the information that you can get from their website, they are going to lower temperature application, not high temperature application. And I understood that the cooling was an issue. But at Antora, it's not so much an issue. We discussed about that. So we should find some solutions about optimizing the system, which is, in my opinion, the big challenge for going to commercialization and to pile up, let's say, performance for all these layers of this system. This is what I understand.
Thank you very much.
Thank you very much for the very good overview of this field. So at the beginning you were talking about the very high power densities of thermophotovoltaics, but then towards the end you were talking about this thermionic enhanced near-field thermophotovoltaics as a way to increase power density. And I guess the reason for that is that you want to achieve high power densities at lower temperatures. But the other option, of course, is to go to higher temperatures, like what Antora Energy is doing. So what are your thoughts about the benefits of drawbacks of these two different approaches to reach good power density?
Well, one issue I see with higher temperature is the same issue that we have with CPV. At some point we end up with these grid losses, and so there will be this issue to be overcome to find the optimum grid and to minimize the resistive losses, because the incident power is giant, and then you may end up with very high currents. Then if any small resistance will kill your efficiency, so there is a huge challenge to be overcome, which has been addressed by CPV people for a long time. And so this is one issue, I would say, for the high temperature, and also another issue for high temperature, but I think they can be overcome. And then there are people on this way. Is also you will need to cool down a lot of the energy which has not been converted by the converter. So you might end up with ideas like for the turbines where you have different layers or different temperature where you could convert it, but then it's becoming very complicated. So I think both of them, they deserve to be addressed and to be tried, and then they could benefit from the progress that we both will make. So I see some drawbacks and also some advantages on the two lines, but I think we should go for them and find solution to these issues.